Good morning, everyone. I am delighted to welcome you all today. Thank you for joining this session. Today, we will be exploring the fascinating world of gas chromatography columns. The presentation is titled Types of Gas Chromatography, GC Columns and Their Applications. Over the next few slides, we'll look at different types of GC columns and discuss their specific uses in various applications. I hope you find this session both informative and engaging. Let's get started. Let's take a closer look at the introduction to GC columns. These columns are really the heart of the separation process in gas chromatography. Essentially, they are what allow us to distinguish between different compounds in a mixture. The separation primarily relies on two factors: the volatility of the compounds, which is how easily they vaporize, and their interactions with the stationary phase inside the column. Now, when we talk about the main categories of GC columns, there are two. First, we have packed columns, which are filled with a solid or liquid stationary phase packed into a tube. Then, there are capillary columns, also known as open tubular columns, which are much narrower and have the stationary phase coated directly onto the inner wall of a very thin tube. Understanding these differences is key, because each type has its own advantages depending on the application. This foundation helps us appreciate how we can optimize separation and improve analytical results in gas chromatography. Now, let's take a closer look at the key components of GC columns. First, we have the stationary phase, which can be either liquid or solid. This phase is crucial because it interacts with the analytes and helps separate them as they pass through the column. Next is the mobile phase, typically an inert gas like helium, nitrogen, or hydrogen. This gas carries the sample through the column and plays a vital role in the separation process. Moving on, the column dimensions are also important. The length of the column usually ranges from about 10 to 100 meters, which affects the separation efficiency. The internal diameter is generally between 0.1 and 4 millimeters, influencing the flow rate and resolution. Lastly, the film thickness of the stationary phase coating impacts how well different compounds are separated. All these components work together to optimize the separation process, making GC a powerful technique for analyzing complex mixtures. Let's take a closer look at some common applications of packed columns. These are widely used in gas analysis, such as detecting permanent gases, which are crucial in many industrial and environmental contexts. They also play a vital role in industrial process monitoring, helping ensure everything runs smoothly and efficiently. Additionally, packed columns are essential in petrochemical analysis, where precise separation of complex mixtures is needed. Environmental gas sampling is another key area, allowing us to monitor air quality and detect pollutants effectively. Now, regarding the construction of packed columns, they are filled with a solid support material coated with a liquid stationary phase. This setup helps separate different compounds based on their interactions with the stationary phase. Typically, these columns have a diameter of about 2 to 4 millimeters and can be quite long, ranging from 1 to 5 meters, depending on the analysis needs. One of the main advantages of packed columns is their high sample capacity. This means they can handle larger amounts of sample material, which is beneficial in many analytical scenarios. However, it's important to note that they generally provide lower resolution compared to capillary columns. So, while they are great for certain applications, they might not be the best choice when ultra-high resolution is required. Connecting this to the broader theme of chromatography, packed columns are a versatile and cost-effective option, especially suited for routine analysis and larger sample loads. Understanding their strengths and limitations helps us choose the right tool for specific analytical challenges. Let's take a closer look at capillary columns. These are narrow tubes that have an inner wall coated with a stationary phase, which is crucial for separating compounds effectively. When we talk about types, we mainly refer to WCOT, SCOT, and plot. WCOT stands for wall-coated open tubular, where the stationary phase is coated directly onto the inner wall. SCOT, or support-coated open tubular, involves a support material that holds the stationary phase, allowing for different separation properties. Plot which stands for porous layer open tubular, features a porous layer that provides high surface area, ideal for specific applications like analyzing gases. The key advantage of these capillary columns is their high efficiency and resolution, making them essential tools in modern chromatography for achieving precise separation and analysis. This all ties back to our overall goal of improving analytical accuracy and sensitivity in our work. Let's take a closer look at the WCOT columns. These columns feature a thin liquid film that is directly on the column wall, which is a key characteristic. They are actually the most commonly used type of columns in chromatography. One of their main advantages is their high efficiency, which allows for sharp peaks in the separation process. This means you can distinguish between compounds more clearly and quickly. Now, because of their efficiency, WCOT columns are especially useful when analyzing complex mixtures. You'll often see them applied in the analysis of organic compounds, where precise separation is essential. They're also frequently used in pharmaceutical testing, ensuring the purity and composition of drugs. Additionally, they're valuable in food analysis, helping to identify and quantify various components. Overall, WCOT columns are a reliable and versatile choice in many analytical scenarios, making them a fundamental part of modern chromatography techniques. Let's take a closer look at Scott columns. These columns have a solid support coated onto the wall, and then a liquid phase is added on top of that support. This design allows for a higher sample capacity compared to traditional WCOT columns. Because of this increased capacity, Scott columns are particularly useful in applications like trace analysis, where you need to load more sample without losing resolution. They're ideal when higher loading is required to detect low-concentration compounds effectively. This makes Scott columns a valuable tool in analytical scenarios, demanding both sensitivity and higher sample throughput. Now let's take a closer look at the plot columns. As you can see, we're focusing on solid adsorbent layers, such as alumina or molecular sieves. These materials are particularly effective because they provide a sturdy and reliable surface for separation processes. They're especially suitable for gas separations, which is a key application in many industrial settings. When we talk about these applications, we're often referring to the separation of light hydrocarbons, like C1 through C5, which include methane, ethane, and propane, among others. Additionally, these solid adsorbent layers are excellent for handling permanent gases such as oxygen, carbon dioxide, and nitrogen. The ability to selectively adsorb these gases makes them vital for various gas purification and separation processes. So, in summary, this slide highlights how solid adsorbent layers are crucial components in gas separation technologies, especially for light hydrocarbons and permanent gases. Let's talk about the stationary phase polarity in chromatography. When we use nonpolar columns, such as those made of dimethyl polysiloxane, the separation primarily depends on boiling points. In other words, compounds with different boiling points will elute at different times. On the other hand, if we have polar columns, like those made of polyethylene glycol, the separation is based on polarity. Here, the compounds are distinguished by how they interact with the polar stationary phase. Understanding these differences helps us choose the right column for separating specific compounds effectively. This concept is fundamental because it directly impacts the separation process and influences the accuracy of our analysis. Let's take a closer look at the applications of polar columns. These columns are particularly effective for separating compounds like alcohols, esters, fatty acids, and various flavor and fragrance compounds. Their polarity allows them to differentiate molecules based on their interactions with the stationary phase, making them ideal for complex mixtures in food, aroma, and fragrance industries. Now, shifting gears to nonpolar columns, these are primarily used for hydrocarbons, volatile organic compounds, or VOCs, and petroleum products. Because they are nonpolar, they excel at separating nonpolar substances, which are common in petrochemical analysis and environmental testing. The key takeaway here is that choosing the right type of column, polar or nonpolar, depends largely on the nature of the compounds you're analyzing. This choice directly influences the efficiency and accuracy of your separation process, which ties back to our overall theme of optimizing analytical methods for different types of chemical compounds. Now, let's talk about how we choose the right column for our analysis. The first key factor is the nature of the analyte. You want to consider whether your compound is polar or nonpolar, because that will influence which stationary phase is most suitable for separation. Next, polarity plays a crucial role. For example, polar columns work better for polar compounds, ensuring better interaction and separation. Then, there's the boiling point range of your analytes. If your compounds have a wide boiling point range, you'll need to select a column that can handle that, possibly with a broader temperature program to efficiently separate all components. Another important aspect is the required resolution. Depending on how closely your compound's retention times are, you might need a column with high resolving power to distinguish them clearly. Finally, consider the thermal stability of your analytes and the column itself. If your compounds are heat-sensitive, you'll want a column that operates effectively at lower temperatures to prevent decomposition. All these criteria are interconnected and essential for optimizing your chromatographic separation, ultimately leading to more accurate and reliable results in your analysis. Let's take a closer look at how capillary columns compare to packed columns. One of the main advantages of capillary columns is their higher resolution, meaning they can separate compounds more effectively, which is crucial for complex samples. They also enable faster analysis times, helping us get results more quickly without sacrificing quality. Additionally, capillary columns offer better sensitivity, so we can detect even trace amounts of analytes more reliably. And finally, they require a lower amount of sample, which is especially beneficial when sample quantity is limited. Overall, these advantages make capillary columns a powerful choice in modern chromatography, aligning perfectly with our goal of achieving precise, efficient, and sensitive analysis. Let's wrap up with the conclusion. First, it's important to understand that the choice of GC column is absolutely critical for achieving separation efficiency. The right column can make a significant difference in how well your compounds are separated and identified. In modern analytical applications, capillary columns have become the standard because of their superior performance, smaller sample requirements, and higher resolution capabilities. They really dominate the field today. Proper selection of the column isn't just about getting a separation. It directly impacts the accuracy of your results, the sensitivity of your detection, and the reproducibility of your experiments. When you choose the right column, you're setting yourself up for more reliable and consistent data. So, in essence, taking the time to understand and select the appropriate GC column is one of the most important steps in method development. It ties everything together and ensures that your analysis is precise, sensitive, and reproducible, which is ultimately what we're all aiming for in our work. For further support, please don't hesitate to reach out to us. We're here to help you with any questions or additional information you might need. Feel free to contact us through the channels provided. And with that, I want to sincerely thank you for your time and attention today. Your engagement is truly appreciated, and I hope you found this presentation valuable. Remember, we're always available to support your efforts moving forward. Thank you once again.